is a video for an answer key to some non-Gaussian calculations and some Gaussian calculations. We'll start off with a line of positive charge that has a linear charge density and is arranged in a semicircle. So since we're in a semicircle, we do not have symmetry, so we cannot use Gauss's law. So we have to use non-Gaussian situation here, but we do need to establish a unique direction. So we want to find the electric field at the origin, which is this point here. So of course, if I look at a dq, a small q here, it's going to be pushing in this direction. And if I have another small dq, I'll be pushing in this direction here. So our y's will cross off, and we'll be left with one unique direction with electric field pointing along the x-axis. Now we have a linear charge density. That's a constant charge density. So lambda does equal q over x. Therefore, q does equal lambda x, and dq then equals lambda dx. That's the differential. Now what about this? Well, we have an arc length. Okay, arc length is given by r theta. So dx can be written as r d theta. Okay, so imagine an infinitesimal small little angle difference here, and we'll have a dx along the arc length then. Therefore, dq is equal to lambda r d theta. Now, our driving integral for non-Gaussian for electric field is equal to dq over 4 pi epsilon naught r squared. So let's fill in what we got. So for dq, we have lambda r d theta, and we'll divide that by 4 pi epsilon naught r squared. And we have to multiply that by the cosine of theta because we want the x direction only for this electric field. So then we have to come up with our limits of integration. Well, our angle theta goes all the way through a semicircle. So we can consider this to be 0 degrees here, all the way to pi over 2. So our limits of integration are 0 to pi over 2. Okay. Pull out all your constants. Electric field is lambda over 4 pi r, or epsilon naught times r. Okay, we have one r crossing off r squared down here to make that r. Integral of cosine theta d theta. Now the integral of cosine is the sine of theta. And here's all of our constants out front. And we're evaluating that from pi over 2 to 0. Well, the sine of pi over 2, of course, is 1. And the sine of 0 is 0. So our ending result is lambda over 4 pi epsilon naught r. Now it asks, what angle would maximize the electric field at the origin? Well, that would be from 0 to pi over 2. This semicircle does maximize it, because if we start to go over here, then we're going to get some effects going in the opposite direction, canceling out electric field in the positive x direction. So that maximizes it. Now what about the electric potential at the origin? Well, we still have the same integral, except now it's the driving integral is dq over 4 pi epsilon naught r, and not r squared. We're going to integrate that. So we're integrating from 0 to pi over 2 of lambda r d theta over 4 pi epsilon naught r. And then the r's cross off. Please notice that voltage is not a vector. Therefore, we don't have a cosine theta there. So we're integrating, all of our constants are out here, pi over 2 of just d theta. Now, of course, the integral of d theta just becomes theta. And we're integrating that from 0 to pi over 2. So I'm just going to put pi over 2 in for theta, then subtract 0. Putting pi over 2 volts is lambda over 8 epsilon naught. Now, what would maximize our potential? Well, an entire circle would maximize that because it would be 0 to 2 pi, and I can put 2 pi in, okay, for my angle. So that's a good example of a non-Gaussian calculation for both voltage and for electric field.